Morning to all. So we'll discuss another derivation, that is a maximum likelihood hypothesis for predicting the probability. That is, so in our context of patient learning, the output we want the probabilities of the hypothesis. Probability we want. So for whether HML is going to give you that type of the probability or not, that you are going to prove here. Okay, so we'll see one of the example before moving to the derivation. One of the medical patient, whether he serves with particular disease or does not serve, how we are going to represent using a discrete output. So this is the function we can represent using a discrete output, that is given the features of the patient. So his output will be either 0 or his output will be or 1 it is. Okay, whether he does not survive, whether he serves. So discrete output exactly we are telling that he serves or does not serves. Okay, so for this type of the application, instead of getting this type of the output, we wish to learn the probability that he serves or does not serve. We wish to learn the probability that he serves or does not serve. Okay, how we are going to represent such type of the function? This f dash is the function where the value of this is probability that f of x is equal to 1. Okay, not directly the f of x is equal to 1 or 0. It is what? It is the probability that f of x is equal to 1 or 0. The meaning is that the probability that he serves, the probability that he does not serves. So that is the value of f dash of x. So one example has been given. 98% patient serves, 2% patient does not. Okay, so what is the value of f dash of x? And this is 0.98 and 0.02. Okay, the probability of, that a patient serves, the probability that patient does not serve. So HML is going to provide us this type of the output, not 0 or 1. So you are going to prove that HML is going to give the probability as our output. Okay, let's start the derivation using what? Using the HML formula. This is the HML formula. So what is the meaning of this? Probability of observing the data with respect to particular, given the particular hypothesis. Okay, so we'll have an expression first for this. Okay, to have that, let us represent D with a pair of values to represent each instance in the D. So x1 d1, x2 d2 up to xm dm, m samples are there, where xi is what? It is a feature set of ith sample, di is what? It is the target value of that ith sample. Okay, so as we already discussed, we can take the individual probability of all these instances and take the product of that to represent this probability. Okay, so that's itself we have done here. D is what? Our xi and di. This is xi and di, and this is the h, product of that, product of individual probabilities of these content with respect to particular h. Okay, so we will have an expression for this first, then we will get this one. Okay, to have this we will use one property called as a probability property. So that is what, if this is the b, comma is here, that's why we are taking this as a b and this as a a. Okay, p of b comma a is equal to p of a comma b into p of b. Okay, so our b is this one, our a is this one. So we are going to represent here okay, so a is what? Our a is what? Our a is this. Okay, di h. Okay, what is our b? Our b is xi. P of b means p of xi. Okay, so we got the expression for this. Okay, so substitute this within this equation, so we will get this equation. Okay, so now we will have a expression for this. This is itself our output actually. So what is that? The probability of getting the value of di for a particular sample xi with respect to particular h. Okay, for example, if the patient survives particular h I am taking, the patient survive, that is of my hypothesis. what is the probability of what is the probability of getting the di from the capital D with respect to given the features of xi? Okay, so this is itself we want as a output. Yes. Okay, so that's why this is going to be represented using the equation this. Okay, the probability of getting di given the particular features xi with respect to particular hypothesis I am observing, we will get a one hypothesis, that is itself our output. So that is the h of xi, that is for a di is equal to 1. For di is equal to 1, you are going to get a h of xi. For di equal to 0, we are getting another probability, that is 1 minus h of xi. So output of this will be probability. If this is a 1 probability for a di equal to 1, this is another probability for di is equal to 0. Okay, so this is what we have represented this using this. I hope you understood this. If you have doubt, please clarify. Okay, now so we can represent this whole expression using this single expression. Okay, so this actually is equivalent to this. Okay, so you can verify here. I need this for di is equal to 1. Okay, di is equal to 1 here, this will represent only this. Di is equal to 1 means this will become 0. Okay, so anything raised to 0 will become a 1 here, so we left with only h of xi, that is equal to this. Okay, so for di equal to 0, you should get 1 minus of xi. So put di is equal to 0 here, 1 minus 0. So 1 minus 0 means raised to 1 it is, we left with a 0. We left with only this. Di equal to 0 means we will be 1 here. So 1 minus h of xi. We left with this. That is equal to this. So this is what another representation of this equation. Okay. So now put this in a previous equation. Okay. So you are going to put this where in this in equation 1 you are going to put that. Okay, so once you put that, okay, you have product symbol here. Okay, so substitute this with the summation by multiplying this with the log that we have done previously. So this will become log of xy. So if it is log of xy, so then it is log of x plus log of y. This is x, this is x, and this is y. So log of x plus log of y. Okay, and next this is what log of x raised to log of x raised to y it is. This is log of x, this is y. So how it become y into log x. So y into log x. Similarly this y into log x. Okay, next. So we got this expression of for p of d. So put this value in our HML formula. So in the HML formula, what arg of uh, you put that here. Okay, so here p of xi is not containing any h parameter. Okay, so you ignore this, you are left with only this. Okay, so how is this expression? Di log of h of xi plus 1 minus di log of 1 minus h of xi. Okay, so we how it this expression is, this is what, this is a product of p1 plus p2, p1 plus p2 is equal to 1, p1 plus p2 is equal to 1, like that it is now. So this is what di is there, 1 minus di is there, h of xi is there, 1 minus h of x is there. Okay, so this is equal to 1 means 1 of the probability. P1 plus P2 is equal to 1 means P1 is equal to 1 minus P2. Like that this expression is. Okay, so that's what it is proved. HML is equal to sum of the probabilities. Okay, yeah, it describes the quantity that must be maximized in order to get the one of the hypothesis. Okay, so this expression will prove that HML is what it is, the sum of like this expression, P1 plus P2 is equal to 1. Okay, So whatever we are getting, the answer for HML is actually the probabilities. I hope if you have any doubt in any of the expression, please inform. Okay, bye.